Yeah, so at the outset, I have to say that I have this unique privilege that I have an academic attachment in one of the universities in the US, and therefore I am sort of routinely able to see the way liver transplant is growing in our country compared to how it is growing in the West. And please trust me that we have no clue how far behind we have gone in the last 2 to 3 years. So machine perfusion has becoming the norm for most centers in the West. Next कैसे आएगा? Sorry. So anyway, so I'll start off with the thing. So we have made great progress in minimally invasive donor hepatectomy and taking on complex living donor transplants and everything. But we are really far behind in disease donor transplants compared to the rest of the world now. So, why do we need machine perfusion? We have, this is the US data, and while there are about 40,000 transplants this is all organs, not just liver. So while 40,000 transplants were done in the US last year, about 78,000 organs were wasted. So twice the number of organs were wasted, not unused, because of several reasons, logistics, unsuitable organs and whatever. But almost twice the number of organs were wasted. So to obviously try to prevent these organ wastage, machine perfusion came in. About 5 to 6 years ago in the Europe, Spain, Netherlands, and the UK were the countries where it started really. In the US, it took a little more time. So about 2 years ago they started, but the change has been like phenomenal, because they went from like 15 to 20% of donors being DCD in the US to now almost close to 50 to 60% of them being DCD. Because once you put it on the machine, they're like brain dead organs, and they function like that. The outcomes are the same. So just to give you a perspective, a lot of us know that kidneys have been pumped in the West for a long time, and I just want you to focus on this modality column and not and the outcomes column. So most of the kidneys that are being perfused are being cold perfused, which is a blue color, which is hypothermic perfusion. Some studies, which also reflects the practice, and some studies and increasingly more centers now are using the hypothermic perfusion with oxygenation for the kidneys. But almost no centers use normothermic perfusion for the kidneys. That's because it's just not cost effective. But having said that, look at the outcomes, and most studies show you that the DGF rates are lower, the graft survival is better, and the kidney function is better. That's what you achieve with machine perfusion, hypothermic machine perfusion, when you do it for the kidneys. Now, for liver, it's like 50-50. There are some people who firmly believe in hypothermic perfusion, and there are others who firmly believe in normothermic perfusion, and they don't talk to each other. But having said that, whether you do hypothermic or you do normothermic perfusion, you will see a reduction in early allograft dysfunction. You will see a reduction in non-anastomotic biliary strictures, which is a problem with DCDs, and increased utilization. Increased utilization is also seen in the kidney, like hugely. In the past, we used to sort of think twice about using a kidney which was more than 12 hours old. Now it's routine that people will use kidneys which are 24, 36 hours old, routinely, because they have been just put on the machine. And then with normothermic perfusion, you are not only able to increase the utilization of the livers, but also you don't have that cutoff of 8 hours or 12 hours for preservation. Now, there are several centers in the US that don't do a night transplant, liver transplants. So the liver will come and sit on the machine all night, and then they start at 8 o'clock. Every single transplant is finished before 5 p.m. So that's how it is changing practice. But in short, the liver is like split 50-50, hypothermic and normothermic. Outcomes are similar, whatever is expected. Early allograft dysfunction is less, biliary complications are less, utilization has increased. As far as heart and lungs are concerned, it's purely normothermic. There is some hypothermic perfusion being used for lungs, but other than that, almost none. It's all normothermic perfusion, because for them, assessment of function is really critical. So when the heart sort of beats on the machine, that's when they assess its contractility and function, and that's when they use it. Again, here it's higher utilization, but no reduction in graft dysfunction. So they're seeing the same kind of graft function that they would see otherwise from DCD compared to brain dead donors. And this is just a summary of the same thing, where different organs are being perfused with different technologies. Different companies have all these machines that they have. Preservation times have started increasing from 4 hours in heart and lungs to about 6 to 8 hours now. In livers, from about 6 to 12 hours to up to more than about 18 hours. Up to 24 hours is actually FDA they have the FDA approval for preserving up to 24 hours, right? So this is just a important background because for the stuff that I'm going to talk later. Having said that, now the important thing is in experimental situations, for heart, the preservation time has been extended to 24 hours. For lungs, 24 hours. For liver, 7 days. So we are looking at off-the-shelf livers now, very soon. And then for kidneys, 48 hours, right? And then, unfortunately, the victim of this is the cost. And each of these technologies are extremely prohibitively costly. We can't afford it. And what's like the cost, this thing? So because hypothermic is cheaper, so for kidney, most studies will tell you that cost is not a problem. So a kidney transplant costs a lot, and then if you add like $3,000 or $5,000 to it, it's not such a big deal. It's possible to accommodate that. Overall, because the cost is not very high with hypothermic perfusion, it overall cost improvement for the program or for the transplant itself is really very high. So it's for kidney transplant, hypothermic perfusion works. It's cost effective. It's going to stay. For liver transplant, if you do it in the UK, which is a national health system, and the machine is partially supported by NHS, the development of Organox, it costs you about £7,000, so about 10,000 now, a little less than $10,000 now. That's comparing the comparison with static cold storage. Having said that, see, in India the cost is for static cold storage is practically just a few lakhs. So therefore, if you did the same study in India, the cost differential would be a couple of lakhs. It won't be, which will be the same actually. $7,000 will be around 5 lakhs or 6 lakhs, right? But if you try to do it with the one in the US, I'm sorry, I didn't put that study here. So the cost of using a machine in the US is almost 40,000 to 45,000 for the Organox, which costs about £7,000 in the UK. And if you ended up going to Transmedics, which is the OCS system, it's about $100,000 to $120,000 per use, just for the disposables. So that's not going to work in India at all because our cost of transplant itself is like $25,000. So therefore, the problem with having liver perfusion, this is liver hypothermic. So these costs are accurate. So I'm going to talk about the other one here in this slide. So when you go to normothermic perfusion, the costs increase substantially. The only way it is affordable is if it's your own machine, like in the UK or in Europe. So because both these machines were made in US, UK and Europe, so therefore for them the cost is really low. It's about $7,000 to $10,000 approximately, which is okay for a transplant in those countries. But if you went to US, this last study, 24 study, and Cleveland Clinic uses the Transmedics system. The cost per use is about $100,000 to $120,000, and that's just not feasible. So to sort of cheat the economic and statistic numbers, what they do is they will tell you that, okay, if you use so many times this machine, and if you increase your transplants by so many number of times, and then your early allograft dysfunction is less, so the amount of money that you're going to spend on managing those biliary complications and early allograft dysfunction has to be subtracted from this. Now, by doing that, they justify that your costs are offset by the complications that you're not having. But that's just not true because it's, most centers that use the machine perfusion, they're losing money with each case that they do. Every single transplant is a loss for the hospital. Right. So this is what we have achieved so far, is the machine perfusion allows you to recover the graft to recover from the hypoxic injury, which happens during the procurement more in a DCD compared to brain dead. It allows you objective assessment of the organ function before you transplant it. It allows you to transplant all these high risk livers, which are extended criteria, very high enzymes and all that, into a patient, knowing that these are going to work most likely. It extends preservation time, and unfortunately, none of these technologies repair the non-hypoxic damage that the graft has. What are the non-hypoxic things that the graft has? Is steatosis. There is a steatosis. Now, putting it on the machine is not going to fix that. But that's what the goals for the future are. So these are the goals that the new things that are happening in machine perfusion world, and we are going to talk about them one by one. So basically what happened is that the Swiss team led by Professor Clavian, they started doing longer term machine perfusion. So they had a company which was supported by the Swiss government called as Liver for Life. And they made a machine which was like a sort of ad hoc made. And when they started perfusing, they realized that after about 48 hours, there is the lactate doesn't clear, which was happening for the first 24 hours. It starts building up, and you can't maintain the graft for longer than that. And then they added a dialysis machine to the circuit, and it worked beautifully. So the lactate would clear now, and the liver was not remaining acidotic. So they sort of figured that out. With time, but then the question was, how do you now assess the function of the liver? Because the only thing that was working so far, so when we started putting these livers on the machine, we were looking at lactate in the blood, we were looking at AST levels, and if both these things were dropping, then we would think that this liver is good. And then some people were studying the bile pH, the color of the bile, quantity of bile being made and all that. And that didn't pan out very well. So a lot of people have stopped using that. But now we have a new challenge, because now we don't really know, if you preserve it for more than 48 hours, what to look for. So in the hypothermic world, they had this thing called as FMN, which is a flavin mono something. So they were found it to be quite accurate, but it performed spectacularly well in normothermic perfusion. So now, and there are certain other things, like there is a scanner which is based on the Raman spectroscopy effect, and that can tell you non-invasively the function of the liver, the mitochondrial function of the liver. So there are several ways that, and you can look at the portal flow, you can look at the hepatic artery flow, the resistance in these vessels, and you can do metabolomics and miRNA, a lot of stuff you can do. But right now we don't really know which of these works well and which of these don't, but we are getting close. I mean, at least for within 24 hours, we know lactate works beautifully. Everything else is out. But for more than 24 hours, we are still trying to figure out what works. So these are the changes that they made in that machine. So one is that they figured that if you keep the liver in the same position for more than 48 hours, then there's pressure necrosis. So you have to keep moving the liver. So it's on a little this thing. Oh, sorry. Can I just continue? Yeah. So they put it on a little hammock sort of thing, and then the pressure will change, so it doesn't get pressure necrosis anymore. Then they realized that the nutrition that you are giving to the liver, which is like a TPN, you had to give it with the circadian rhythm. So you have to give it during the day and not during the night. And then you had to put it on dialysis and all that. So there are several things that we realized, and they changed in the machine, and now that works pretty well. So the next step was to actually split the machine on the liver on the machine. And with that, and if you also added growth factors to the circuit, then you would see liver regenerating. So now you split the liver into two, and then you have two lobes, which each of them is regenerated and hypertrophied a little, and then you can use it in two recipients. So that's the next thing that they're achieving, and there are several pathways that they are targeting with their growth factors. So, and then again, assessment of this liver in the long term is still a challenge. So it's not completely sorted, and there are various functional tests, various hemodynamic parameters and histopathology tests that we are looking at as to which one to follow and which one is reliable. This is the what their machine looks like. It's a very sort of crude design right now, but they're also doing defatting cocktails, some stem cell therapy, some CRISPR-Cas genetic modulation on these livers, and making the untransplantable livers into transplantable ones. The defatting work is quite at advanced stage. I think it's like all sorted. What is the cocktail is all sorted now. It's not come to clinical use, but it will happen very soon. The other thing that has happened is, as you were aware, that eGenesis supplies all the pigs that are being transplanted in the US for xenotransplants. So now they have done a collaboration with Organox, and recently they've got FDA approval for this. So basically what happens is that the pig's liver goes onto their machine, and then it's on the circuit. So you can hook it to a patient who has acute or chronic liver failure or acute liver failure, and provide the support that in the past the Mars and the ELAD systems were supposed to do, and this appears to be more promising than that. But you can also test drugs on this machine. And once you do that, then your drug development cycle, which used to be years, like 10 to 15 years, because you had to go to small animal, large animal, primates, then human trials. Now you're directly doing it on human livers. So therefore, the drug development cycle has gone from a couple of decades to a couple of years with this now. This has not been done for livers, but this has just been published last year. So you could basically, we know that the blood group, all blood groups are derived from antigen H, which is their basic antigen. So what they do now is that they will sort of do enzymatic conversion of blood group A kidneys to blood group H. So once your antigen expressed on the surface or blood group H, then it is like a universal donor. So basically, you can convert any group organ to blood group H, and then you can use it for any patient you want. And so they tried it both on normothermic machine as well as hypothermic, and they realized that if you did it on normothermic, in 2 hours, your organ can be converted into blood group H organ. Whereas if you did the same in hypothermic, it takes about 12 to 24 hours. And then the last thing is ischemia-free liver transplant. This is being pioneered by a center in China, in Guangzhou. And almost all papers are written by this guy called as Go, because he's the only English-speaking guy in their team. And basically, they use the same machine, the normothermic machine, and they will I went there to see some of their cases, and basically what they do is they'll just put the donor into a OT, and once the liver is out, it's not perfused with any solution. It's continuously getting perfused while it is removed from the donor's body, and it goes on the machine, and then they'll wheel the donor out, bring the patient into the same OT, and then they will do the hepatectomy. The liver will sit there for 4 to 6 hours. The lactates will go from 10, 12 to 1 to whatever. And then they will continue the circulation and put it in the recipient. That's because they don't have a battery in their system, because they copied this from the ex vivo system machine, and their own machine doesn't have a battery yet. But once they put a battery in, then you can actually do donor and recipient surgery simultaneously and get even better. So they have done RCT on this, and the results are phenomenally well. And because there is no ischemia reperfusion injury at all, they get less rejection. Everything is better. So this is where the future is, and the world is headed. And with all these circuits are sort of sorted now. You can do pharmacological therapy, gene modulation, cell therapy, nanoparticles, everything on this. This is going to happen very soon. And like I said, you can do a lot of interesting things. We will see this in clinical practice probably in the next 5 to 10 years. So that's the summary of everything that's going on. And, we can do a lot of exciting stuff. Thank you very much.